Good morning, everyone. This morning we're going to be talking about Cantor's ternary set, and we're going to talk about it specifically about how it affects physics, not mathematics. I understand the mathematical interpretation is about, sets, infinite sets, and all those infinite sets are between 0 and 1, and I understand what the mathematicians are saying, and I'm not disagreeing with them. But there's a much more intuitive, direct, and simple explanation that makes it fit into physics. And I keep hearing mathematicians talking about wanting to find bridges between math and physics and the way things are, and this is one of those bridges. This is one of those connections that are absolutely undeniable once you see it and you understand it. So you've heard me talk before, if you've watched any of my videos, about a new interpretation for a Dirac's equation, which is polarity on this line, no, or none, neither, 0/3, and both 3/3. Negative charge on this side, positive charge on this side. Negative charge is 1/3, and positive charge is 2/3. And the reason that we have this output is very simple. When you start defining fields, you find that I found that using vector fields and the way that science tries to define it as divergence and curl just is complicated, doesn't make a lot of sense. I know that's all you have, but there's a better way. If you take, and this is in field theory, so I've covered it before. If you want to go watch the short video on fields and 11 dimensions revealed, 3 dimensions makes Euclidean space, 6 vector dimensions require 8 cubic spaces, which then give you 3 transitional planes. The first transitional plane, if a particle is down on the page, is this plane of density. Then you have plane of charge and plane of polarity, where negative and positive are on either side of the plane of charge, and monopole, dipole is on either side of the plane of polarity. And what this does is really just breaks up your plane of density into quad outputs on top. And it's because of the kinetic and potential energy that creates this plane of density where this particle, the core of our field, I believe that fields all radiate from a core, ends up making the quad outputs, which can be defined by Dirac's equation. Dirac's equation had 4 outputs, not 2. It's not just charge, it's charge and polarity. And these become the next 2 transitional planes in our 8 spaces around 6-dimensional vectors. And it may sound complicated, but it's really not once you see it and you understand it. The thing is when you want to go and define Dirac's equation as quad outputs, the breakthrough for me didn't occur until I realized that he was talking about thirds. So negative charge is 1/3, positive charge is 2/3. Then you have no thirds and 3/3 being neither and both. And the thing is if you take this interpretation, right, but you want to see it by someone who knows what they're talking about, right, and you want a full understanding of how we got to one the other, neither and both as the output to Dirac's equation? And the answer is Cantor's ternary set. And I know that this is not the way that mathematicians talk about it, but just watch. Cantor's ternary set, just for those who aren't caught up on it yet, is just a line. And what Cantor says is if you cut this into thirds and drop these two down, right, that you now have the beginning of an infinite set. And the way that that works is this is 0, this is 1, this is 1/3, and this is 2/3. And the thing is those end pieces never actually go away, which is why it becomes an infinite set. And what isn't on this line will never be on this line, and what is on this line will be here permanently. So this becomes 2/3 and 1. This becomes 1/3 and 0. But then you take each of these shorter lines and you drop them down, right? Cut here and here, and now you drop down this one and this one. This one is 1/3. This one, or actually this goes to ninths, but as you break it down, this breaks down forever. So I understand what they're saying. I know where they're going with it and why they're getting there. And this is the way that mathematicians define Cantor's ternary set. But there's a better way for physicists to define Cantor's ternary set. And the way this works is very simple. You take a line, same thing, cut it in thirds, right? And now before you do anything else, I'm a physicist, right? I'm a theoretical particle physicist. So there must be space, there must be a place for things, things must actually move. There is no infinities, there is none of this. Everything is real. So I can't move something unless there's a space to move it. So while this single line cut into thirds is fine with me, you can't drop these other two ends down unless there's a space to do that, right? In your own mind, think about that for a second. And down here, let's just create that space. You have 3 line segments up here, and if you're going to move any of them, you have to have a place to move them. I mean, that makes sense. It's logical, right? So you create 3 spaces down here in order to move them. Now, in Cantor's ternary set, right, what you do is, and we're going to draw another one here, cut it into thirds again, and then when you move it down, we have the spaces, it moves into here and here. And this, whoops, is solid, but these two vanish. So what you really have, and I'm going to draw this one over here again because I didn't do it very well there. This is 3/3. All 3 are on one line, 3/3. This is 0/3. All 3 spaces for the 3 lines exist, but there are none there. So it's 3 here and 0/3 here. This, and again, I if you drop the end pieces down and they go away, becomes 1/3. And the 2 that you've dropped down, right, they become 2/3. So how do you take Cantor's ternary set to define Dirac's equation? I mean, Cantor's ternary set literally interprets Dirac's equation, his real equation with 4 outputs. And it does it as 3/3, no thirds, 1/3, and 2/3. And that's it. That's the whole thing that we're going to try and cover today. And here's the thing. For those of you who don't know, there is something called a Mandelbrot set. This is the Mandelbrot set in its visual form, right? And Mandelbrot looked at this and he said, basically that geometry in the way that we look at it does not define nature, because it is all straight lines and angles. And if you look at a cloud, or water spilling over a dam, or the shape of a river as it goes somewhere, nothing about those are squared or perfectly angled. In fact, what you really have is constant change. So he said geometry works, but there's got to be a better way to define it. So he came up with the Mandelbrot set. And this is showing the Mandelbrot set in its visual form, which is basically that it just simply repeats again and again and again. And he based the Mandelbrot set 100% on Cantor's ternary set. And so if you go, and we'll flip back here real quick, to the way that they look at Cantor's ternary set, it's an infinite series between 1 and 0, or 0 and 1. And if you look at Mandelbrot, it's reflected. Every one of these is reflected smaller, and then smaller, and then smaller, and it repeats again and again and again at every magnitude. So while I'm not saying that that's incorrect, I'm saying that that shows the magnitudes in physics, right? From below quantum mechanics all the way up to quantum mechanics. Physics doesn't believe that anything is smaller than, quantum mechanics, than quarks and the smallest things that make up atoms. I believe it goes on below that. I call it the subverse, then the atomiverse, as it builds larger and larger. But there are verses on top of verses on top of verses on top of verses. And this is the stacking of all of those. And it is 100% based on Cantor's ternary set. And that's the bridge that I was talking about. How does that work? Well, Cantor's ternary set being the basis of the Mandelbrot set. I'm sure all of you have heard of this company called Pixar. They took the Mandelbrot set, which is basically the basis of a new kind of geometry. Like I was saying, Euclidean geometry is all angles and straight lines, and that's just not the world that we see. So Mandelbrot created a new kind of geometry to explain exactly what we're seeing. And Pixar, fractal geometry is what it's called, and Pixar, the people who were working on fractal geometry, quit and went to Hollywood and started making, graphic cartoons using fractal geometry. So if you want to know how something as old as Cantor's ternary set can lead to modern day billions, this is it. I mean, Mandelbrot based 100% of his understanding of the Mandelbrot set on Cantor's ternary set. And fractal geometry is based 100% on the Mandelbrot set. And Pixar were the people who were working on fractal geometry, which is based on Mandelbrot, which is based on Cantor's ternary set. Holy. So you get this billion-dollar company that is 100% based on fractal geometry, which is 100% based on Mandelbrot, which is 100% based on Cantor's ternary set. And what I'm telling you is that the output to Dirac's equations are 0/3, 1/3, 2/3, and 3/3 in the way that I've defined here. No thirds, 1/3, 2/3, and 3/3, where no thirds and 3/3 are polarity, and 1/3 and 2/3 are charge, and that is the output to Dirac's equation, which sits exactly on top of that plane of density. So this is the plane of density as, right? Polarity and charge sit on this plane created by the kinetic and potential energy. So what's happening on this plane is also what is defined in the Lagrangian, the Hamiltonian. They're defining the kinetic and potential energy that fight back and forth across this plane of density. And if you set Dirac's equation directly on top of that, it looks like this. Polarity and charge as outputs defined 100% by the Cantor ternary set. Now, again, my interpretation exploded in my mind when I realized that positive and negative charge are not equals. One is 1/3, one is 2/3. And that immediately became no thirds and 3/3 for polarity. And that immediately became the output to Dirac's equations as interpreted by the Cantor ternary set. So the leading geometric, fractal geometry, the leading geometric theories tied directly to the surface of orbital fields, and orbital fields are Schrodinger's wave function. I explain them better because I understand the internal, the 8 cubic spaces, the 6 vector fields, the 4 circular vector dimensions, from accelerated particles defined by Einstein. So all of it fits together, and the key that unlocks it is Cantor's ternary set. Plain and simple. You get the exact description, and I realized that it was no thirds, 1/3, 2/3, and 3/3 before I even understood that it was the Cantor's ternary set. When I saw Cantor and listened to them talk about their infinities, I was like, wait a minute. I understand what you're saying, but this is completely the surface of this field, the output to Dirac's equations. So if you're looking for a bridge between the latest, newest mathematics, fractal geometry, and the Schrodinger's wave function, which is my orbital field, then this is it. You get the latest mathematics with the deepest interpretation of quantum mechanics, of Schrodinger's wave function. And it cannot be simpler to me. The way you look at this, 3/3. The line is all 3 of them in the same spot. Before you move any of them, before you drop these down, there must be a space to drop them down. To any particle physicist, we have to have spaces, we have to have particles. So the spaces must exist before you move them. All 3 lines up here, all 3 spaces here. When you go ahead and drop them down, you end up with 1 above, 1/3, and 2/3. And the reason that this is so important is because the output here to Dirac's equation is in base 9. So while this is 0, it's not none. It is neither 1/3 or 2/3. So when you hear statistical probabilities and you hear them, the rule that zero statistical probability doesn't mean it won't happen, and 100% statistical probability does not guarantee it happens, They're statistical probabilities. 0 is neither, not none, and there's a good reason for that. The statistical probabilities I just told you is the reason. And 3/3 doesn't guarantee it, it just, it's statistical probability. So these no thirds, 1/3, 2/3, and 3/3 are the statistical probabilities. And it's funny, this is the output to the double slit experiment. On the back wall, behind the double slit, which there's another video on the double slit experiment if you want to watch that. But the output on this back wall of this double slit experiment, waves coming through here, waves coming through here, they interfere here, and you get these dark line, little bit lighter, much lighter, much lighter, almost none, almost none. Well, these are the statistical probabilities. This is 3/3, 2/3, 1/3, 0/3. And then 3/3, 2/3, 1/3, 0/3. So what you're seeing is the orbital field, the output to Cantor's ternary set, as it defines Dirac's equation on the surface, on this plane of density that's created by the orbital field, you're seeing that on a linear frame on the back wall. And this same interpretation, right, is why when you fire an electron through just one hole, right, you still get these lines along the back. And they're still 3/3, 2/3, 1/3, no thirds. They're still those because the wave function, right, no thirds, 1/3, 2/3, and 3/3. Cantor's ternary set, as the interpretation of Dirac's equation on the surface, on this plane of density, is simply carried with the electron when you fire it through this hole. It's internal to the particle. So this is Cantor's ternary set, which is the basis of the Mandelbrot set, which is the basis of fractal geometry, the cutting edge of geometry in the modern world, tied directly to the most advanced interpretation of quantum mechanics. It's Schrodinger's wave function, but defined as my orbital field. So it's all here, and it's so simple, I don't know how you can't see it. I mean, it's got to be one of the simplest ways to explain the statistical probabilities of quantum mechanics.